Blood is the principal medium for delivering and distributing materials by convection throughout the body. In circulatory systems, blood is distributed throughout the body in tubular structures, the blood vessels. These form complex networks of tubes, and their architecture is tied in closely with their function. To understand how these blood vessel networks are built, we have to address two questions. One is how the entire system works. That will involve delving quite deeply into the physics of moving fluids within the body. The second is how well the networks of vessels are constructed to do what they are supposed to do. We can phrase this question another way. What are the design principles that govern the operation and efficiency of circulatory systems? Circulatory system architecture follows certain common rules. The first is that the architecture is commonly a so-called ramifying or branch tree structure. In other words, a large parent artery, or trunk artery if you prefer, branches and feeds blood into smaller daughter or branch arteries. These, in turn, branch themselves into ever more and smaller arteries, and so forth and so forth. In animals with a completely closed circulatory system, like vertebrates, this recurrent branching culminates in so-called capillary networks, which are built more like a so-called reticulated or net-like network of vessels that connect the arterial and venous systems together. We'll have more to say later about the detailed architecture of capillaries. The circulatory system has to do two mutually incompatible things. It must efficiently distribute the blood from the pump, namely the heart, throughout the body. At the same time, it has to ensure the effective delivery of materials like oxygen or nutrients to all of the body's ultimate customers, so to speak, the cells. I say these two processes are mutually incompatible because the architecture for efficient distribution is much different from the architecture for effective delivery. Efficient distribution means distributing blood in large vessels where the blood moves quickly and with little loss of energy. Effective delivery means having innumerable tiny vessels that can deliver the blood into close proximity to every cell of the body. What makes for effective delivery makes for inefficient distribution, mainly because it takes a great deal of energy to force blood through all those tiny vessels. On the other hand, vessels that distribute fluids efficiently, that is, with little loss of energy, minimize the delivery of materials from the blood to the surroundings. As it turns out, the branch tree architecture that is common among circulatory systems is the most effective way to resolve these mutually contradictory needs. That's a pretty bald-faced assertion, and we're going to spend a little while working out the rules that underlie this assertion. Our first step, though, is to understand the physics of moving fluid through tubes. We start with a basic fact from physics. A parcel of fluid, whether it's air, water, or blood, has mass. In the case of fluids, mass is usually represented as density, ρ, with units of kilograms per meter cubed, or something else dimensionally equivalent. When a parcel of fluid is set in motion at velocity u, it acquires momentum, which is the product of the density, the volume of the parcel, and the velocity. A body of fluid can be thought of as many parcels of fluid that flow with respect to one another. In this conception, it's not really appropriate, of course, to talk about a parcel of fluid in isolation from every other parcel around it. The movement of one parcel necessarily affects the movement of every other parcel around it. Let's illustrate this idea with an important concept, the concept of fluid shear. Let's imagine a sheet of fluid which we designate with a numeral 1, set in motion so that it has some momentum W. In a mass of fluid, that sheet will be adjacent to some other sheet of fluid, here designated with the numeral 2. Let's assume that sheet 2 is still initially, that is, it has a velocity of 0 and hence momentum of 0. Parcel 1 will therefore move parallel to parcel 2. This particular type of motion is called shear. Imagine now that there exists a kind of frictional force between parcel 1 and parcel 2. The shearing motion in parcel 1 will therefore impart some of its momentum to parcel 2, setting it in motion too. This transfer of momentum in fluids has a special name, viscosity. This example makes two important points about what viscosity is. The first is that viscosity is fundamentally a transfer of momentum within fluids subject to shear. The greater the rate this transfer of momentum is, the higher will be the fluid's viscosity. You can think about this in terms of the analogy of fluid friction. Higher frictional forces mean higher transfers of momentum, which means higher viscosity. The second point is that fluids can have momentum, but they may not necessarily exhibit viscosity. You can find tables of fluid viscosity in places like the Handbook of Chemistry and Physics, but this does not make viscosity a fundamental property of the fluid, like its mass would be. Viscosity only arises when fluids are subject to shearing motion. Let's formalize this idea a little bit. We plot two quantities with respect to one another. On the vertical axis is the shear stress, which is the momentum gradient within a fluid subject to shear. It is the ratio of the differential of momentum over the differential of distance. On the x-axis is the so-called shear rate, which is the velocity gradient within a fluid subjected to shear. It is the differential of velocity over the differential of distance. In fluids generally, the faster the shear rate, the faster will be the transfer of momentum. In a simple fluid like water, this increase will be linear. That is, the plot of shear stress and shear rate will produce a straight line, and the viscosity is the slope of this line. The steeper the slope, the higher the viscosity will be. Maple syrup, or honey for example, will have steeper slopes than water. The viscous behavior of blood is a little different from this. The plot of shear stress and shear rate does not produce a straight line, for example, but the basic idea is the same, and we'll explore these differences a bit more deeply in another lecture. For now, let's just turn to what this simple concept of viscosity means for flow in enclosed tubes like blood vessels. In blood vessels, flow is confined to a tube. One important feature of flow through tubes is the so-called principle of continuity. This simply means that the volume flow of blood into one end of the tube must equal the volume flow out the other end of the tube. This might seem like a trivial concept, but once we get into flows in branched networks, it will be very important. Volume flow of blood through a tube imparts a certain momentum to the fluid, but confining the flow in a pipe necessarily involves the transfer of momentum from the flowing fluid to the stationary tube wall. This is where the viscosity of the fluid becomes significant. Parcels of blood in the center of the tube have a particular velocity and therefore a particular momentum. At the inside surface of the tube, in contrast, the fluid's momentum is zero because it is adhered to the immobile inside surface of the tube. This is known as the no-slip condition, and it means there will necessarily be a transfer of momentum from the flowing blood to the tube. This transfer of momentum will impose a so-called velocity profile on the blood flowing through the tube. For a simple fluid like water, this velocity profile will be parabolic. This tells us that the shear stress and shear rate varies with respect to the distance from the center of the tube to its inside surface. Specifically, blood flowing in the center of the tube will experience almost zero shear. We see this by the relatively flat tangent to the velocity profile. The tangent, of course, represents the velocity gradient within the tube, that is, the shear rate. At the center of the tube, viscosity plays almost no role in the flow of fluid because there is almost no shear force operating there. Shear rate and shear stress increase the closer you get to the inside surface of the tube and is maximized at the tube wall. This behavior leads us to a fundamental physical equation that describes the energetics of fluid flow through tubes. Imagine a tube of length L and radius r, with the fluid flowing through it at a volume flow rate V dot. Imagine also that the fluid is forced through the pipe by a so-called head pressure, P sub n. We know that the pressure in the pipe will diminish as fluid flows along the pipe, and at the point where the fluid leaves the pipe, the pressure will be P sub out. We know that pressure must diminish because there's a transfer of momentum from the fluid to the vessel. Loss of momentum means loss of the potential energy that can drive fluid flow. This loss of energy is reflected in the drop of pressure. We won't go through how this fundamental equation is derived, but here it is. It's called Poissier's law. It simply states that the mass flow rate of fluid through the tube is equal to the ratio of two products. In the numerator is the product of pressure difference, delta P, pi, and the pipe radius raised to the fourth power. This latter term is very significant. If all other terms of this equation are held constant, for every doubling of pipe radius, the flow rate of fluid through the tube will increase by a factor of 2 to the fourth power, or 16. In the denominator, we have the product of 8 times the length of the pipe times the viscosity. This tells us that for every doubling of the length of the pipe, given that all other terms remain equal, the flow rate of fluid through the pipe will be diminished by a factor of 1/2. A similar scaling relationship applies to variation in the viscosity as well. For every doubling of the viscosity, the flow rate of fluid through the tube will be diminished by a factor of 1/2. Okay, that covered some pretty tough ground. The hard work will pay off, though, because Poissier's law is the starting point for the fundamental physical analysis of how blood flows through networks of circular tubes. It won't be the complete answer. For example, although Poissier's law applies pretty well to most of the vessels of the vascular system, it doesn't describe flows through the very small capillaries particularly well, even though it puts a pretty powerful tool in our hands. So let's put it to work.